So let me get going with the Piazza questions that I got. Hang on. All right, so here is something about table conflicts with the answer to the self-check. I'll look into that, but so let me get into this issue real quick. And so so we always want to contrast how an array performs versus a linked list. So I have an array. And now in an array, if I want to look at the kth element, so if this here is k, so I just say a bracket k, and that happens in constant time. So internally in the processor, it takes the starting address of the array, it adds k times the number of bytes per element to it. So that's a very simple arithmetic operation. It has this address. It looks up in memory what's at that address. It's just a few steps in the processor, and it doesn't matter what k is. So it's clearly O of 1. And now you have a linked list. And so we ask, what does it take to get to the kth value? And the answer is, it does kind of depend. If you are at the beginning of the linked list, and now you want to look at the kth value, so now you want to call like get of k, then you have to step over k minus 1 links. So if you're initially here, you have to call next, 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 next in a loop until you're finally there. So that's going to be, we can surely say it's O of k. It takes k times some constant amount of steps. And then if k is completely arbitrary, if it could be any value between 0 and n, where n is the length, I should say 0 and n minus 1, where n is the length of the array, then on average, k is n over 2, if k is in fact completely arbitrary, and then this would be the same thing as saying O of n, where n is the size of the container. But there are two assumptions. Assumption number one, that we're currently that we're not anywhere near k. And assumption number two, that k could be anything. So if I asked you, what is the efficiency to get to any of the first 10 elements of a linked list? Is it O of 1 or is it O of n? So let me write this on it so that, so what is, this would be a great exam question. So what is the big O efficiency, big O, to get any of the first 10 elements in a linked list of length n? So O of 1, O of 10, O of n. And so here the insight is O of 10 is the same thing as O of 1. It's some constant time. And it really doesn't matter how long the list is, so it seems kind of unlikely that it's going to be O of n. So if you have a list of 1,000 or a list with 1,000,000 elements, if all you care about is the first 10, you can just look at all of them. Yeah, it might take a little while to look at all of them, but it's a constant amount of effort. It does not grow if the list gets longer, so it is O of 1. Now, the other thing is, suppose you have a loop where you go through a linked list you look at the first one, then you look at the second one. Let's say you want to sum up all of the elements in it. Then you go to the third one, and so on. So when you look at, traverse the linked list in this linear way, and then, yes, it does take O of n to get to an arbitrary element, and if you were to do it n times, you might say, well, that's O of n times n, or O of n squared. But that's not really true, because in this situation, you're not visiting an arbitrary element. You always visit the next one. And to visit the next one is fast. So it really is n times O of 1, or O of n, because you're not visiting an arbitrary element each time. If it was a different algorithm, well, you do have to visit an arbitrary element. Say binary search. Right? Binary search, you would have to visit the one in the middle. And and then you might have to back up and visit one here. Then it would be a more difficult scenario. So it's one would have to think harder what it means to do, say, binary search in a doubly linked list. But it still works. So it would be O of n, in fact, not of O of log n, like it is with an array. But if you just make and that's the complexity that you're going to be seeing on an exam, where you might make a linear traversal, then that is it's n times an O of 1. If, on the other hand, I'm asking you to go to the middle element of a linked list, then you do have to skip past n over 2, so that's O of n. So now it's possible that I muddled up this, or that whoever wrote this quiz, so I'll have another look at this quiz. But maybe not. All right, the first half of page 732. Hang on. Chapter 16. Yeah, well, I'm going to do that today. All right. And this question got answered. All right, so if you have other questions, just put them on here, and I'll deal with them after the lecture. So let me get to today's lecture, and that should answer that first half of 732. All right, so today we're going to be talking about the humble array list. And so an array list is just an array, but better. Internally, an array list manages an array, and so it hides the resizing of the array from the user. So here you see the array list object has two instance variables, one that gives the current size. In this case, that would be 3, because this happens to hold 3 elements, and the other one is an array to the elements. So it's an array of objects here. And so you can see this thing has 3 elements in here. And then there's a bunch of empty slots. So one calls this array that's managed by the array list the buffer. And it's always true that the buffer length is at least as large as the size of the array list. It usually is a little bit larger so that you have room to add extra elements. So to access an array element is totally trivial. You simply get to the buffer and you say, what is that element? Well, you want to check the bounds before, so I wrote a little helper function here to check the bounds, that if it's out of bounds, it just throws in an exception. It's constant time, so checking the bounds takes a bit of time. Getting to a particular value takes a certain amount of time, but it's a fixed amount of time. Doesn't matter how long or how short the array is. So it's O of 1. Setting is the same thing. Let's look at removing. Well, when you want to remove something from an array list, then you need to remove it from the buffer array. And as you know, removing means you have to shift stuff down. So let's say I want to remove this element, then I just have to move all of these elements down. Well, how many do I have to move down? Well, if I remove the kth element, then I have to move down n minus k, or maybe n minus k minus 1. And now again, you kind of need to know what k is. If k could be completely arbitrary, then there's an equal chance that it's any of those n positions. And so on average, k would be n over 2, and n minus n over 2 would again be n over 2. So on average, you would move n over 2 elements. You know, sometimes you might be lucky and remove mostly at the end, but on average, it's n over 2. And so again, a single remove then costs on average O of n. If your array is 1,000 elements long, you have to move about 500 elements. If it's 1,000,000 elements long, you have to move 500,000. So it's proportional to the length of the array. And so now one could have a thought experiment and say, you know, removing seems awfully expensive. And it's a common operation. Could we make removal cheaper by doing the following? Instead of removing, can I just put a null in here? That would be constant time. You would just find the thing, put a null in there, and it's gone, right? So what's wrong with that idea? What's that? Yes, now all my indexes are off, and now if I wanted to implement get, I couldn't simply go to the kth element, but I would have to start at the beginning and count how many non-null values I find, and then get would have now become O of n. So it's a trade-off. And probably not a good trade-off in this situation. But so when you're talking about the efficiency of these operations, it really depends, you know, if you re-implement one of them in a particular way, that might throw off a different one. So this turns out not to be a good idea because we expect to do gets and sets much more often than to do removes. But and if you needed to do a lot of removes, you'd probably be better off just with a linked list, because having this thing filled with nulls is no picnic either. All right, it was just a thought experiment. All right. So now I have a hopefully simple clicker question. So remove last, you will want to implement it in terms of remove by simply calling remove with the last index. And so here's my question about it. So how fast is it? Is it O of n? Because it calls remove, and remove is O of n. Is it O of 1? Is it O of n squared? Is it O of log n? So I added a plausible explanation to each one of them. 3 of them are BS, and 1 of them is good. Sorry. All right, 48. What did I do? All right, let's see. So, so remove last calls remove, and remove is O of n. We just had that. So it seems plausible that it can't get any faster, right? So if you call something that's O of n, surely that's the time it must take. So I thought that sounds pretty good. Number 3 is got to be wrong, because what's the efficiency of size? So when you look at the implementation, size will almost surely just return this current size thing, and that's a constant time operation. So it doesn't seem plausible that size would be O of n. And so that can't be wrong. Right. And even if it was true, then it wouldn't work out, because if you first call size, and even if that was an O of n operation, and then you call remove, and that's an O of n operation, that's still O of n, because you're doing something that's proportional, and then you do something else that's also proportional to n, and you just add them up, so that doesn't give you an n squared. You would get the n squared is if you have a loop where n times you do something that's O of n. But here you're just doing it twice, so there's no plausible reason for 3. And 4, well, yeah, that doesn't make any sense, right? Because we're not cutting anything in half here. So it's between 1 and 2, and so we need to figure out which one it is. And so it is true, because when you remove the last element, let's see what we do. In this case, this loop turns out to do absolutely nothing, because there's nothing that we need to copy. And so we only really do 4 steps. Check bounds, capture the contents, decrement current size, and return. That's a constant number of steps. Doesn't depend on how long the array is. So, and that's what I said before. You have to always look at context. You have to say, in the specific situation, n is not, the thing that we remove, the index, is not totally arbitrary. It's the last one, and removing the last one is in fact fast. Removing the first one is always slow, but removing the last element in an array list is always fast. All right, now let's get on to adding. Adding is the hard part. So, if you add in the middle, we know what happens. Adding in the middle shifts elements, and it's just like removing, so it's going to be an O of n operation. So on average, you will have to move half of the elements if you add in the middle. Adding at the beginning is got to be slow, because you have to move all of the elements, and that's clearly is also O of n. What about adding at the end? Adding at the end is kind of free, provided there's room. So if you look at the picture here, if I need to add something else at the end, then it just goes in here. The next one goes in here, next one goes in here. All I have to do is keep incrementing this index and moving something into wherever that index points. So that's a fixed amount of computation, one increment, one store at a known location, O of 1. So adding at the end is O of 1, except, of course, what if the array is completely full? What happens with an array list when it's completely full? Does it throw up and say, I can't take it anymore? No, it quietly increases its size, right? So, and I should have put a picture in here, but so I'll just have to draw it. So what happens is you have the existing array list, and now it makes one that's twice as long. Copies over all of these elements. then it reroutes that this one now becomes the buffer, and then the old one will eventually be garbage collected. So that copying is, of course, expensive. Those are n copies, so it's an O of n operation. So we have this funny situation that the cost of an addition depends on when it happens. So instead of looking at the cost of one addition, let's look at the cost of n additions. So this implementation happens to start with an array of size 10. So the first 10 calls cost, let's say, $1 each. So the first 10 ones are $1 per call. Then in the 11th call, oops, we have a penalty. We have to pay $10 penalty. So now our total cost is $20. And then we pay $10 again, one at a time. And oops, there's another penalty for $20. And then for the next 20, we get to pay $1. And out of sudden, then we have to pay $40. And it's a little confusing. We don't really know what is the total cost. And so the way to think about it is the piggy bank. So here's how the piggy bank works. So I'm going to sell you an add operation. And every time, I'm going to charge you $3. So you're going to pay me a fixed cost for each add. You will never have to pay a penalty. And here's how I make a profit. So the first time you pay me $3, I add the element, costs me $1, and I put $2 in the piggy bank. And I do that for the first 10 calls, in fact. So I've received $30. I've expended $10 to store those elements and $20 in the bank. And now that fateful call 11 comes. I get the penalty. I will absorb the penalty. I won't charge you. I'll just take $10 from the piggy bank. There's still $10 left in the piggy bank. You paid me $1. I used that. No, you paid me $3, right? So I use $1 to do my insertion and put another $2 in the piggy bank, like I always do. So that gets me to another 10 calls. And now I have to pay $20 penalty. Well, I say, do I have enough money in the piggy bank? Yes, I do, because in the last 10 calls, you paid me $30. I needed $10 to make the 10 calls, and I take the 20 to pay the penalty. Then there's going to be 20 calls over which I collect $40, and I have to pay a $40 penalty. I come out okay. Then there's going to be 40 calls where I collect $80, and that's the penalty that I later have to charge. So in other words, if I always charge you a little bit more ahead of time for each ad, then for you, each ad is constant cost. It costs the same amount. You don't even know or care where you are. And that is exactly how you can justify that on what's called an amortized basis, where you take into account the cost for n consecutive calls. Each one of them has constant cost. So, and we say it's almost the same thing as O of 1. It's just, it's O of 1 with this little amortization twist, and so they use the plus symbol here. It doesn't mean it's any more expensive than O of 1. It just means that every once in a while there is this big cost that one had to pay into a piggy bank for to be able to absorb it. So it's a fixed cost. It's a little bit more than $1, but it's $3. It's not like more expensive the bigger the array gets. So that's a very interesting and useful idea, just to look at the cost of a bunch of operations when they happen one after another. And if once in a while you have to restructure your data structure, to see if the cost of that restructuring can be divided over the cost of the cheap operations. And that's business. As that's like when you use a credit card and everyone pays for the small number of people who fraudulently get free stuff and all of that. So it's amortized over everyone. It's the same thing here. All right, so let's just have a quick review here of what all these various costs are. So if we want to add something at the end of a data structure, then we've just seen for an array list that's amortized O of 1. To remove from the end is also amortized O of 1, because what happens is when you eventually want to shrink down the array list again if you make lots of removals, and you have to pay for that. But you can make it so that you can absorb the cost by distributing over the other removals. And here the key is, as it turns out, you would think that you shrink it back down when it's only 50% full, but that turns out not to be enough. You have to wait until it's only 25% full. And then you'll be able to recover the cost. So with doubly linked lists, we know that adding and removing at the end is also very cheap. We have a reference to the end, and we just reroute the links around there. With a singly linked list, even assuming that you have a reference to the end, adding is O of 1, but removing cannot be O of 1. With a singly linked list, removing at the end is expensive. Adding at the head, here the situation is kind of reversed. And for an array, that's very expensive. You have to shift all the elements. For a linked list, for any kind of linked list, adding at the head is trivial. You just add a link and make that now the new head. Adding in the middle, for an array, it's expensive, for an array list. And for a linked list, it's cheap provided you're already there. So if you already have an iterator that points to just where you want to insert in the middle, then it's an O of 1. If you first have to move the iterator there, then it's also O of n. So the only cost saving for a linked list is if you're doing some kind of surgery where you're already having your iterator, you're already looking around to find the right spot where you want to insert, and now you're just concerned about the cost of the insertion itself. For a linked list, that is cheap, because all you have to do is add a link like this, add a link like this. Let's say it's doubly linked. So 4 steps. All right. So let's apply these. So I want to add a 0 directly in the middle of something. If the sequence has even length, or if it has odd length, I just want to replace the middle by a 0. What data structure should I use for maximum efficiency? Oops. All right, so the majority opinion is it doesn't matter, and then there's a strong minority for a set. Why can't it be a set? A set is an unordered collection. A set has no positions. There's no such thing as the middle of a set. Okay, with a set, order doesn't matter. Yes, if it's a tree set, it can be traversed in sorted order, but even that, of course, is not very interesting because with this particular example, then the 0 would always come first. So it can't be a set. So why doesn't it matter? Well, if you have an array list, to insert in the middle, it's easy enough to compute the middle. It's just the length over 2. But then the insertion costs you an O of n operation because you have to move half of them. So and since you don't know which of the two cases it is, whether it's even length or odd length, we're going to have to assume it's O of n. With a doubly linked list, if you were in the middle, then the insertion would be instantaneous, would be an O of 1 operation. But to get to the middle takes you n over 2 steps. So it's also O of n. So assuming you've just been given this one thing and you have to carry out this one operation, then it really doesn't much matter from an efficiency point of view. If you had to do something like that multiple times, then it might be a different story. All right, so it looks like most of you kind of getting a good intuition here. Oh, wait. Oh, I see. So actually, no, I did fool people. Or maybe if people got confused by my keys here. So it doesn't, let me amplify this. It does not matter. So with an array list, you pay for moving the elements. That's O of n. And for the doubly linked list, you pay for finding the middle, and that's O of n. So either way, it's an O of n operation. You pay for different things. Yeah?
You can argue that maybe an array list would be better on the off chance.
Sure. So you could say with an. Oh, all right. So here are the rules for this. From a big O perspective, it doesn't matter. But it could matter for any number of other reasons. It could just be that the shifting is just so laborious that a linked list will always be faster. Or the other way around, it might be that maybe there's a hardware instruction to do the shifting and it's actually fairly fast, whereas the hopping thing is slow. So at this point, that means that you have no easy way of choosing between one or the other. You would have to actually implement it and time it if it mattered, or count instructions or something. So the big O analysis doesn't really help you when two things have the same big O. At that point, you would have to look more closely. So for example, there's this algorithm that... Did we talk about insertion sort? I guess not. There's another O of n squared sorting algorithm called insertion sort. We talked about selection sort. And insertion sort and selection sort are both O of n squared. But it turns out that if you have a very short list, less than 10 elements or so, insertion sort is actually blazingly fast. And so the way that the library sort works is if you just call it arrays.sort in Java, it calls a merge sort, except if the list has less than, I think, 7 elements or fewer. And then they switch to insertion sort. So, and how they got to that number, they must have timed it. So for the big O analysis tells you what goes on for large items, and it tells you whether one thing is overwhelmingly better or worse than something else. So if you have an O of n log n algorithm on 1,000,000 elements, it's almost surely going to be bound to be better than an O of n squared algorithm on 1,000,000 elements. Unless, of course, what if it does an enormous amount of time? You can't even totally guarantee that. But for like the kind of normal algorithms where that do more or less the same kinds of steps every time, you can surely say n log n is better. But you do have to, if you have two O of n log n algorithms, one of them could be much faster than the other or much slower. And so you kind of then have to look at the individual instructions. And so here, I have no good intuition whether shifting 500,000 elements is any worse than it is to hop past 500,000 links. I wouldn't know. I would have to build both and see what happens. All right. How are we doing on time? I think it's probably useful, given that these things are going to be in the exam, if I run through one more example of some big O stuff. So let me do that. So the problem that I have in mind is the following. I have a sequence of numbers, and you should think long sequence of numbers, hundreds of thousands. So, I have 1 million digits of pi, say. And now I want to know what you've always wanted to know about all those digits of pi, the first 1 million of them. Which of them is the most common? Is it really true that the number 6 is 3 times as common as the number 2? Maybe because for some devilish reasons. So I want to find out which is the most common number in a long sequence of numbers. And I want to do it, first of all, I want to find a solution. So how the heck can I find out which one is the most common number? Well, I guess the obvious thing is, I look at the first number here, and I just go and count. How often does it occur? And then I could put that, maybe I'll build up a second parallel array, and I'll put those counts in here. So I'll count how many ones. And I put that in here. And then here I'll count how many 4s. And I'll count here how many 9s. And so I fill up this parallel array with all of these counts. So I might find out that there are 17,219 1s and 18,311 4s and only 793 9s, because for whatever reason there aren't that many. And so I would do that for all of the various numbers here. They don't have to be single digits. I could have a number 13 here as well, depending on what the application is. I just have lots of them. And so I would count them all. And then I would go through this array of counts, and I would find the maximum. So let's say this one is the max. And then I would look up north and say, oh, my most frequent one was the 4. In fact, it occurred 18,300 so many times. So think about it, that'll work. Every time that I see a number, I count how often it happens. I put that count next to the number. I take the maximum of the counts, I look up, and that's the most frequent number. And in fact, I even know how often it occurs, which I wasn't asked, but I could tell if someone asked me to. Now let's see how efficient is this algorithm. First of all, we need to find out how efficient is it to count how many times k occurs, where k is some number, in a sequence of n values. So let's just focus on the sub-problem first. So I have an array of n values, n is presumably large, and now I want to find out how many of them are 4. How do I do it? I ask the first one, are you a 4? The second one, are you a 4? Are you a 4? And each time I find a 4, I increment a counter. So if I have 1 million elements, I have to look at 1 million elements to see if they're a 4. If I have n elements, I have to look at n elements. So it's an O of n I make a linear walk through n elements, looking at each one of them. That's O of n. Now, I do that counting not once. I do it for the first element, the second, the third. For every single one of those n elements, I run count. So, I do that n times. So the cost of that repetition is n times O of n, or O of n squared. So if I have a million elements, I now have to do, goodness, 8 trillion operations, or some multiple thereof. That doesn't sound so good, actually. And now finally, I have to find the maximum of all of these counts. If I have n elements, I have n counts. How long does it take to get the maximum of n elements? I look at the first one. I look at the second one. I look at the third one. Each time checking whether it's bigger than what I think is the maximum. I look at all of them once. So that's again O of n. So now my total is O of n squared plus O of n, which is O of n squared, because the n squared dominates. So there, I have found an O of n squared algorithm that gives me the most frequently occurring value. And so in general, when one does this, it says, well, that's nice, at least it was an O of n cubed. But on the other hand, could we do better? So one of the things that's wasteful in this algorithm, if you think about it, is that over here, I'm counting the number of ones again. Right? Because the number 1 occurs again. And you would say, can I avoid those repetitive counts? And the answer is, of course you can, because what you could do is you could look backwards and you could see whether that thing already occurred. But in general, if you think about looking backwards, if you're somewhere in the middle, near n over 2, and it wasn't there, if this number was in fact there for the very first time, that looking backwards takes you O of n steps, takes you n over 2 steps. That's really no better than a count that also takes you O of n steps. So it's not going to really change the O of n efficiency. That's unfortunate. If you knew there were only digits, then you could keep a separate list of 10, and that would be better. But if they're arbitrary numbers, you really might have to go backwards all the way to the beginning. So so if they're not just digits but arbitrary numbers, that's probably not going to help you. Give me another idea that might make it simpler to solve this. They're numbers. Numbers of any size, not just digits, but numbers. Or with strings, it would be the same thing.
Well, I was thinking if you just go through and apply, can you just have a switch statement for all the numbers?
If they're only digits, if they're only the digits 0 to 9, then I agree. Then all you have to do is you count how many zeros, how many ones, up to how many nines there are, and you can do it in O of n time. But if they're arbitrary numbers, like if one of them could be 2 million.
What if you make your second array that long?
Now that's a good. So with integers, you could say, well, there's this finite number of integers, right? There's only 2 billion integers, 4 billion, 2 billion, 4 billion, I think, integers, and so could you make an array of 4 billion counters and then say it's random? I guess you could, and maybe in a few years when memory has become so incredibly cheap, we would say that's a legitimate strategy, but today one would still say that's probably not right. And of course, if there were strings, that wouldn't work. You might want to know, what is the most frequent string in Alice in Wonderland? It's probably the or Alice or some such thing, but you might want to know. And with strings, there's an infinite, or there's such a very large number of them that you couldn't easily have a counter for every one. So what is one way that would make this problem easier? Yes?
Sort it first.
If I sort it first. All right. So now after sorting, let's say there are no 3s. And so after sorting, now my list looks like this. And now, in fact, I can make a linear pass, and I can say, right now it looks like the 1 is the winner, and I keep a single counter and count how many 1s I've seen. So I've seen 13,105 25 ones. Now I see the 2, and I say, so this is my winner. Maybe I also need to have 1 for the current. So that's right now the 2, and then the 2 maybe gets up to 21,205, and then I say, oh, that was the winner. And now I look at the 3 for the current, and there's none. And then I look at, so I wouldn't even look at it. I would look at the 4, and I would find 2 of them or so. And so I would have variables for the longest sequence that I've seen, and for the current sequence that I'm looking at. And once in a while, I find a longer one, and I update the winner. But I make a linear pass through the entire array in this fashion. So this pass is an O of n pass because I need to look at every element only once. Hey, I found an O of n algorithm instead of an O of n squared. That's big. That's a huge improvement. Almost. I did have to sort. How much does it cost me to sort? N log n. Yes. So I have O of n log n plus O of n, and that is still O of n log n. But in this case, you can see the sorting is surely worth it. It's to go down from O of n squared to O of n log n is good. The sorting was worth it. All right. So what does that mean? You have to have you can memorize some of these big O things. You can memorize, sorting takes O of n log n, and you could memorize that insertion and removal in the middle of an array is O of n. But at some point, you also need to have intuition. And there's right now 3 pieces of intuition that you need. So intuition number 1 is a linear traversal with constant work per step is O of n. If you visit n elements and you do the same amount of work, no matter whether it's little or a lot of work, the same amount of work at each step, that's O of n. So that would be, for example, computing the sum of a sequence, finding the max of a sequence, counting matches. All of those where you have a single loop that looks at every element once and does some amount of operation, those are O of n. The other, that's kind of your bread and butter case. Number 2 is if the operations that you do are very simple. If they just involve a small number of steps, then they're fixed cost. So a small number of steps is O of 1. So for example, add at end of a linked list with a tail pointer. If it doesn't have a tail pointer, it's a different story. But if you have a pointer to the tail, then adding means you go to the tail, you allocate a new element, you move a couple of links. Maybe it's 10 steps, maybe it's 20. It doesn't matter, even if it's 100. But it's a constrained number of steps. It doesn't depend on whether the list is this long or this long. And the third case that you may come in is that if you have a loop of n steps, and each of them takes O of n, then the whole thing is O of n squared. There are many situations where that happens. The one that we've just seen, you call count, which itself is O of n times. Selection sort is like that. At each step you call max, which is O of n, and you do that n times. Is O of n squared. And so those are kind of the three intuitions that you need at this point. Later in 146 you're going to see a few more interesting examples where more stuff happens, but that should carry you through the exam. So make sure you do those assignments that I wrote up on Piazza. People ask, do I give out solutions? I wasn't going to give out solutions, but if you have questions, then by all means put those on. All right, let's see if we have any remaining Piazza questions. Any way to follow up? Okay, let me actually make very sure that everyone understands this. So there was a quiz question that says, you are in a linked list or in an array list, and you have a current position. What's a position? In an array list, a position is an integer index k. In a linked list, a position is an iterator. So they're the moral equivalent of each other. And now you want to go to the next element. So over here, that means you want to go to the element with the index k plus 1. Over here, it means you want to look at the next one over here. And someone said, it's O of n. And so I hopefully nipped that in about right away and said, no, it's definitely not O of n. It's a constant amount of work. It's a small handful of steps. Over here it's, one addition and maybe one lookup if they wanted us to know what the value under it was. Here it was, one looking up a pointer and then maybe looking up in the data field if they wanted us to know it. It's a small number of steps each time. It's O of 1. Either way, it's O of 1. If one asked, what is the cost of traversing the entire structure and looking at all of the elements? Of course, that's O of n each time. But that's making one iteration, then that's O of 1. All right, that's all I got. Let's finish the lab. Yeah? Oh, yeah. Yes. Okay, so I understand what you're saying. So this is for the homework that says implement a reverse operation that takes a linked list like this. Singly linked? I think singly linked. So we don't have backward links. and you're given some number k, and now you're supposed to reverse the nodes by directly manipulating the links. No iterator, no helper methods, no nothing. It's just you and the links. Okay? So this is bound to be an unpleasant problem. Right? So, and in fact, really singly linked? That was mean of me. Ew. Yeah, that is totally mean. So let's see what we want to achieve, and then you'll see why I say that was not very nice. I mean, now that's what I put out. So what we want to achieve is we want these links to go this way. We want what a great problem. We want first what used to point to here, we want it to point to here, and we want this one to go to here. Is that a fair statement? Okay, well, we've faced adversity before, so here's how you do it. So I'm going to keep a pair that I call like n. Well, I'll just call it n1 and n2, where n2 is always the next one. Okay, and so in each, and so I have to figure out how to update them. So in each step, what do I have to do? Is I have to say n2 dot next equals n1, right? That gives me the red link here. And now I need to and then I need to make it so that I can move. Now I just overwrote n2 dot next. That wasn't so smart, so maybe I'll need to have one that's n3 here that points here. Because then I can say n2 equals n3, n3 equals n3 dot next. So that in the next iteration around, they're still again in that same configuration. So ponder that, and maybe do I need n1? I think I need n1. One might be able to eliminate one of them once one understands this, but a scheme like this will work, where you keep these references, and then you do your surgery, the rerouting of the links, and then you move the entire thing over by one step, so that in the next step that picture is repeated and they're now all one over. So there's those three references, n1, n2, and 3. That way you can move your way forward through the linked list without having to actually build like a stack of backwards links. So you can do the surgery step at a time. It can be done. It's a great problem.
Oh, that's that one more.
Yeah.
For the stock, the first problem.
Yeah.
When we, the test cases, do we ever have it when we'll be selling a whole entire stock? So let's say you buy 100 and your sell is going to be like 50?
Sure, could happen.
Okay.
The only thing that I said, you're not going to sell more than you own.
Yeah, question.
Yeah.
Can you use a list? That separate list?
You cannot use anything. It's you and the raw links. No helper function, no separate data structures, nothing.
Just the methods are received.
No methods. You cannot call methods. You write a single method. That method has a loop, no extra data structures, no nothing. You just rearrange the links. It's just you and the links in the jungle. Okay? The whole idea of this assignment is for you to manipulate those links directly. You are not given a doubly linked list. You're only given a singly linked list. You cannot use a doubly linked list. You have to add it to the singly linked list of section 16.1. You cannot change that list in any way except to add on this one method, which may not call any other methods. Did I mention that? And you can't have any other data structures. It is you and a mess of links and nothing else.
You can't have a linked list inside it.
You cannot have a linked list inside it. Right? So you need to figure out, and really the picture is pretty good. You have the black arrows, and you want the red arrows. And it's obviously doable a step at a time. You first switch the arrow over here. Then you switch the arrow over here. Then you switch the arrow over here. You just need to have enough context to still keep going. Yes? I'm sorry? To what?
You asked if you make a bunch of nodes and just put them in different directions.
Yeah, that's exactly what you do. You need to change the contents of the next fields. So you leave the nodes alone, and you leave the data items alone. You just change the next fields around so that they point to the previous one. And the only thing is you need to be able to keep on going, right? Because as soon as you route the next field, well, how are you going to go forward? You have to have some other variable into which you cleverly have put a copy of the forward reference. So that the picture that I've drawn here, I think where I say keep 3 consecutive references will surely work. So I think once you code it up, you can see that you can dispense with one of them. But I think when you first think through it, that's bound to work, and then you can simplify it after you've gotten it to work, or just leave it like that. But having the 3, you can definitely do it. And so you want to change the like I said, the black links to the red links. You want to leave everything else in place. It's just an exercise that's supposed to make you practice manipulating these links. No one gives a care about reversing the list. But I do care that you have some practice with manipulating these links. Now, someone asks me, does anyone ever actually do this stuff? And does anyone, would Microsoft hire you to move around links in the linked data structure? And the answer is, of course not. It's the same thing as with sorting. Now, we had a whole module on sorting, and it wasn't that you will ever discover a better sorting algorithm, or even ever write another sorting algorithm. You'll just use the library sort, of course. But these are pretty fundamental operations, and by getting some ability to understanding what goes on under the hood, you can later reason about more complicated data structures. Now, there was actually a time when I thought, gosh, no one ever needs to know about these data structures. It's useless. They're all implemented, and it really doesn't matter with these links. But then a few years ago, I all of a sudden had to learn about some of these data structures again, because what's happening now is that with concurrent programming, where your program wants to take advantage of multiple processors, people are right now starting to think differently about the way data structures are used. So it used to be you would have a set, you would add more and more stuff into a set, and each time the set would change. It would get bigger or smaller sometimes you might remove something. Same thing with the map. It would be this mutating thing, But when you have lots of processors, mutating is bad. Because when you have multiple threads mutating the same data structure at the same time, and they don't do it in a coordinated fashion, the various links start pointing into the wrong places. And so mutation is truly bad. So now people are inventing these data structures where instead of adding to a set, what you get is you get a new set that's just like the old one, but it's a completely new one with that extra element. Of course, the old set and the new set share some data. And so to understand that, out of sudden, one has to understand where these links go. And so after 20 years of not having to care about the links, I all of a sudden had to worry about, again, how the stuff works. So it was probably not such a bad idea that they taught it to me 20 years ago. So no one likes these links because they make your head hurt. They're difficult. They are easy to get wrong, and when you get them wrong, they're a mess to debug. But it is something that is actually of some value. So get through it. Yes? We are not learning about multi-threaded programming in this course, but I would totally urge you that if later on there is some kind of an optional course about concurrent programming, go and take it. It's a very useful and important thing. And if I were to today have a job, hire someone fresh out of college and ask them job interview questions, that would be what I would ask questions about. So in this course, we have enough to chew off, and that would just add an extra wrinkle to it. But it's a very, very important subject now because that's where processors are going. They're not getting any faster. We're just getting more of them. All right. Other questions? All right. Let's move on to the lab. Let's try to finish the lab. If you can't finish the lab, it's probably a good idea to do that at home in preparation for the exam. That question that problem that you're doing here on the lab is pretty closely related to one of the exam things. Also, I made a small mistake on one of the testers. So if you haven't gotten to that point yet, at the end of lab 6C or D, I don't quite know where it was, there's a tester. In that tester might not actually show the failure of the code. It will, however, do that once you add the line in here that it says on Piazza. All right.